Right now, in a quiet building at NASA's Jet Propulsion Laboratory in Pasadena, California, a small group of engineers is preparing for something they have never done before. It is a plan so risky that they refuse to try it first on the spacecraft that matters most. Instead, they are testing it on its twin, just to be sure it will not cause permanent damage. If this plan fails, it could speed up the death of the farthest traveling machine humans have ever built. But if it works, if every calculation is correct, if every part responds the way it should, if hardware that is now 49 years old cooperates one more time, it could give us a few more years of information from the only machine we have ever sent into the space between the stars. The engineers have given this plan a nickname. They call it the Big Bang, not because it is graceful or poetic, but because of exactly what it involves. It means changing, all at once, the way electricity moves through every working system on Voyager 1. Not one step at a time, not a slow, careful shutdown followed by a restart. Everything, all together, in a single coordinated switch. And they are attempting this from a distance of 16 billion miles, across a radio link so long that a command takes 23 hours just to arrive, and the reply takes another 23 hours to come back. One shot, one window, no do-overs, and time is running out. To understand why this moment matters so much, you have to understand what Voyager 1 actually is today. Not the legend of it, not the poetic image of a golden record floating silently through the dark, but the real physical truth of what this machine has become and what it is still managing to do. Voyager 1 is 16 billion miles away from us. It travels at roughly 38,000 miles per hour, a speed that sounds incredible until you remember that, even at that pace, it would take more than 70,000 years just to reach the closest star. In August 2012, it crossed the heliopause, the outer edge where the sun's influence finally gives way to the pressure of interstellar space. That made it the first human-built object to actually enter interstellar space, not just approach it. Today, this very day, Voyager 1 is drifting through the plasma that exists between stars, measuring an environment that no instrument had ever measured directly before it got there. It launched in September 1977. Its original mission was supposed to last 4 years. It flew past Jupiter in 1979 and Saturn in 1980, and then, according to the plan, it was supposed to go quiet. Instead, it kept talking. The data kept flowing. The discoveries kept piling up. And the team, back on Earth, a team that has gotten smaller over the decades as older engineers retired and were replaced by younger ones who had to learn programming languages from the 1970s just to communicate with the spacecraft, kept finding new ways to keep it going. Every single year, for 49 years, they have squeezed a bit more life out of a power supply that has been shrinking by about 4 watts annually since launch day. 4 watts a year. Less than the output of a dim light bulb. Gone every year. Forever. When Voyager 1 launched, its 3 power generators, which turn heat from the slow radioactive decay of plutonium into electricity, produced about 470 watts. Today, in the middle of 2026, that number sits closer to 250 watts, under half of what it started with. And that number will never rise again. It can only fall because the physics behind radioactive decay does not bend for anyone. Plutonium-238 has a half-life of just under 88 years, which means that roughly every 88 years, half of what remains stops producing usable heat. Voyager 1 is 49 years into that slow decline, and there is no way to reverse it, slow it, or pause it. It is one of the most predictable processes in all of physics. 7 of Voyager 1's original 10 scientific instruments have already been switched off. Not because they were broken, although a few eventually did break, but because there simply was not enough electricity left to run them alongside everything else the spacecraft absolutely needs in order to survive. Heaters, the radio transmitter, and the onboard systems that prepare and encode data before sending it across 16 billion miles of empty space all draw from the same shrinking pool of power. Every watt saved by turning off a science instrument becomes a watt that keeps the spacecraft itself alive. These shutdown decisions were never made in a panic. Years earlier, the science and engineering teams worked out a careful order for which instruments would go dark and when, designed to get the most possible science out of the spacecraft before the power ran out. In a way, they were writing a plan for a slow, gradual ending, making sure every valuable measurement had already been taken and sent home before it arrived. That plan was holding steady for years. Then, on February 27, 2026, something unexpected happened. It was meant to be an ordinary maneuver, a small adjustment to how the spacecraft was oriented in space, something engineers had done successfully hundreds of times before. The command was sent, the spacecraft confirmed it, the maneuver began, and then the power levels dropped. The drop was not huge, but on a spacecraft where the safety margin is already measured in fractions of a single watt, any unexpected loss of power is not a small problem. It is an emergency. That is because Voyager 1 has a built-in safety system from the 1970s that automatically kicks in whenever the spacecraft tries to draw more power than its generators can supply. This system does not check with anyone first. It does not wait for engineers on Earth to study the situation and respond. It begins shutting things down on its own immediately to protect the spacecraft. And because of that 23-hour communication delay each way, there is absolutely no way to step in and stop it in real time. By the time engineers on the ground even learn something has gone wrong, the automatic system may have already been making decisions on its own for nearly a full day, decisions that might not match what the team would have chosen, decisions that could shut down the wrong systems in the wrong order, or in the worst case, damage something the mission cannot survive without. The team at JPL understood exactly what that power drop on February 27th could mean. Rather than wait to see what would unfold, they acted immediately. On April 17th, 2026, engineers sent a command permanently shutting down the low-energy charged particles instrument, known as LECP, a device that had been running almost continuously since the spacecraft first launched 49 years earlier. This instrument measured charged particles and cosmic rays both from inside our solar system and from the interstellar space beyond, giving scientists priceless information about the structure of the region between the stars, information that, since 2012, had no other source anywhere near it. Kareem Badruddin, the mission manager for Voyager at JPL, spoke about the decision in careful, measured words, the kind people use when doing something painful but necessary. He said that shutting down a science instrument is never anyone's first choice, but that it was simply the best option they had left. Not a good option. The best of the difficult ones available. Voyager 1 now runs with only 2 working science instruments: the plasma wave detector, which picks up vibrations in the plasma of interstellar space, and the magnetometer, which measures magnetic fields. Just 2 instruments remain out of the original 10 that once made up the most ambitious science payload ever sent beyond our solar system. But the engineers left one tiny thing running inside the Shutdown LECP instrument, a half-watt motor. Barely anything at all, but left on for a reason because of what comes next. That reason is the Big Bang Plan, a name the Voyager team came up with themselves. The idea grew out of a question the engineers had been wrestling with for a while. After shutting off 7 of 10 instruments, after turning off heaters for parts considered non-essential, after rewriting software around a damaged memory chip using programming languages most people alive today have never even heard of, what else could possibly be done? Where does the next bit of savings come from? Their answer was not to shut off anything else. Their answer was to completely rethink how power moves through the spacecraft in the first place. Voyager 1's electrical system, like the rest of the spacecraft, was designed in the early 1970s, following the engineering habits of that time. It was never built with the kind of efficiency a modern spacecraft would have. There are wires and pathways moving electricity in ways that made sense when there were 470 watts to spare, but that waste precious energy now that the budget has shrunk to 250 watts and keeps falling. Some of those pathways could be rerouted to remove inefficiencies that used to be harmless, but that now represent the difference between an instrument staying alive and going dark forever. The Big Bang is a plan to reorganize all of these power pathways at the same time, not gradually, not one piece at a time, but everything simultaneously in one single coordinated operation. The reason it has to happen all at once rather than in stages is that the individual changes affect each other. If engineers changed one pathway and left the rest untouched, the spacecraft could pass through a temporary, unstable state that might trigger the automatic safety shutdown, exactly the outcome they are trying to prevent. By making every change at the same moment, they avoid those dangerous in-between states and move directly from the old setup to the new one. By any measure, this is an extremely risky thing to attempt on a 49-year-old spacecraft with no backup system, no way to send repairs, and a communication delay that means it will take nearly 2 full days to find out whether it worked or destroyed the mission. The team is fully aware of this. They have spent months running simulations, checking and rechecking their math, and debating every possible failure scenario. And before trying it on Voyager 1, they decided to test it first on its twin. Voyager 2 is a slightly different spacecraft. It actually launched 16 days before Voyager 1, back in August 1977, but it followed a different path, one that took it past Uranus and Neptune before heading out of the solar system. Because of that longer route, it is now closer to Earth than Voyager 1, sitting at about 13 billion miles away rather than 16 billion. It crossed the heliopause in November 2018, 6 years after its twin, and it has slightly more remaining power, which makes it a somewhat safer choice for testing something completely new. The Big Bang procedure is being tried on Voyager 2 first, with tests scheduled through May and June of 2026. If those tests succeed, if Voyager 2's power system behaves the way the simulations predict, if no safety shutdown gets triggered by accident, and if the new setup delivers the savings the team calculated, then the same procedure will be attempted on Voyager 1 no earlier than July 2026. Matt Hill, the lead scientist for the LECP instrument at the Johns Hopkins Applied Physics Laboratory, did not hide how much rides on this attempt. He said the team is hopeful that this new plan from the Voyager engineers will let them switch the LECP back on aboard Voyager 1 so they can keep discovering whatever unexpected things are still waiting in these far-off regions of space. Coming from someone who has studied this instrument's data for years, that hope is not empty optimism. It is built on nearly 5 decades of evidence that this spacecraft keeps turning up things nobody predicted. There have been plenty of surprises already. A strange, steady humming signal detected in the plasma since 2017 was something no scientific model had anticipated. A region near the heliopause with temperatures over 50,000 degrees Fahrenheit, and a place expected to be cold and mostly empty, defied every prediction. An unexpected magnetic link between the sun's field and the wider galactic field was also something nobody saw coming. Every one of these discoveries came from instruments scientists were not even sure would still be running by the time they made them. That history is exactly why Hill's hope carries real weight. If the Big Bang works on Voyager 2 in June, and then works again on Voyager 1 in July, the power freed up by the new system could be enough to bring the LECP instrument back to life. That is precisely why that tiny half-watt motor was kept running even after the instrument itself went dark, a small, deliberate gesture holding the door open just enough in case there is a chance to walk back through it. While the Big Bang is being tested and refined, Voyager 1 keeps moving. On November 18, 2026, at 2:16 in the morning Pacific time, it will pass a milestone no human-made object has ever reached. It will be exactly 1 light day away from Earth. That is the distance light itself, moving at 186,000 miles per second. The fastest speed anything in the universe can travel, covers in a full 24 hours, about 16.1 billion miles. A message sent from Earth this morning would not even arrive at the spacecraft until tomorrow morning, and any reply would not make it back to us until the day after that. A single question and its answer will take a full 48 hours, 2 entire days, round trip. Think about what that actually means for the engineers working on this. Every diagnostic check, every instrument test, every command meant to adjust the power system or check how it responds now costs 2 full days just in travel time before any real analysis can even begin. When the power drop happened back in February 2026, during that routine maneuver, the team did not learn about it right away. They had to send commands, wait, receive answers, study them, send more commands, and wait again. Making sense of what had happened and deciding what to do took days, not hours. And because the spacecraft's automatic safety system could trigger at any moment, every one of those days mattered enormously. This is the environment the Big Bang will be attempted in. A procedure nobody has ever tried before, on hardware older than almost anything else still operating, separated from mission control by a gap so wide that not even light can close it quickly. The engineers cannot watch this unfold in real time. They send a command, they wait nearly a full day. They get a response, or they do not. And if something goes wrong, it will already have been unfolding for almost a day before anyone on Earth even knows. To really understand what is at stake scientifically, it helps to look closer at that strange, steady hum detected in the plasma since 2017, one of the least explained findings of the entire mission. It is a constant, ongoing signal that has shown up in the data year after year across more than 930 million miles of interstellar space. This finding was published in a respected scientific journal and studied by multiple research groups, and to this day, nobody has fully explained it. There are 2 leading theories. One is that the signal comes from naturally vibrating plasma particles reacting to their surrounding electromagnetic environment. The other involves a different kind of noise, created by the random thermal motion of electrons, which would require scientists to rethink their models of interstellar space far more significantly. Figuring out which explanation is correct requires either more detailed data from Voyager 1 over time, or an entirely new mission built to investigate this question. Until it was switched off, the LECP instrument had been helping narrow down these possibilities by measuring particles alongside the plasma wave readings. With it gone, scientists lose the ability to cross-check that data. If the Big Bang succeeds and the LECP comes back online, that cross-checking becomes possible again. This matters for more than academic curiosity. The interstellar medium is essentially the ocean our solar system moves through, and its density and structure directly shape the strength of the heliosphere, the bubble of solar wind that shields every planet from harsh cosmic radiation. If that medium is more turbulent than current models suggest, the heliosphere is likely far more variable than assumed, and the radiation environment that shaped life on Earth is less stable than we previously understood. Right now, there's no mission ready to take Voyager 1's place. This single fact underlies everything about why the Big Bang attempt matters so much. Once Voyager 1 finally falls silent, likely sometime in the early 2030s based on current projections, there will be nothing left in interstellar space to replace it. There have been proposals within NASA for a dedicated interstellar probe, a spacecraft built specifically to study this region with modern instruments instead of 1970s technology. The scientific case is strong, but as of 2026, it has no funding and no launch date. It exists only as an idea on paper. Even under the most aggressive possible trajectory, a spacecraft launch today would take roughly 25 years just to reach the heliopause. The gap between Voyager 1's final transmission and any replacement would not be measured in months or years, but in decades. During that gap, the flow of information simply stops. The steady plasma readings, the magnetic field measurements, and the particle data that let scientists build a coherent picture of conditions beyond our sun's influence all go silent. The mysterious hum will stay a mystery. The map of interstellar space that Voyager 1 has been slowly filling in will stop being drawn, left unfinished. This is the real reason the Big Bang matters. It is not just about saving one instrument. It is about stretching out for as long as possible the only real-time stream of information we have ever had from beyond our solar system before the silence that is coming. Even so, the Voyager team has faced situations like this before and found their way through. In November 2024, a routine command meant to activate a heater accidentally triggered the spacecraft's safety system, switching Voyager 1 from its main radio transmitter to a backup one that had not been used since 1981, more than 4 decades of sitting dormant. Almost nobody currently working on the mission had ever operated that backup system, yet the team figured it out and restored communication. Back in late 2023, Voyager 1 began sending back garbled, unreadable data for months. Engineers eventually traced the problem to a single failing memory chip, worn down after nearly 50 years of cosmic radiation exposure. Fixing it meant rewriting the affected software and splitting it into pieces stored across different sections of memory, essentially rebuilding part of a computer's logic from 15 billion miles away through a communication loop that took nearly 2 days per exchange. It took months of careful work, but it worked. Before that, there were thruster firings that succeeded when they had every reason not to, and instrument shutdowns carried out perfectly without ever triggering the safety system. Power budgets have been recalculated again and again as the generators kept fading. 49 years of problems that looked unsolvable and solutions the team somehow kept finding anyway. The Big Bang is simply the latest chapter, the boldest and riskiest one yet. November 18th, 2026 is approaching fast, the day Voyager 1 crosses one light day of distance from Earth. The Big Bang test on Voyager 2 is happening right now, in the summer of 2026. If it succeeds, the attempt on Voyager 1 follows in July. Between now and November, we will finally learn whether it worked, whether the LECP instrument comes back to life or stays dark forever, and whether Voyager 1 has bought itself more time to keep speaking to us, or has begun its slow, final fade into silence. What Voyager 1 is doing right now, sending information back across 16 billion miles from a place no instrument had ever explored before, asking questions about the structure of space that directly shape our understanding of the environment. Life on Earth depends on, ranks among the most meaningful scientific efforts happening anywhere, on this planet or beyond it. Nearly 50 years ago, engineers working with slide rules and paper calculations built a machine they expected to last 4 years. It has lasted 49, and it is still going. They built it to carry a golden record filled with whale songs, human laughter, and greetings in 55 languages, sending it into the darkness in the hope that something out there might one day find it. They never built it expecting it to make discoveries, to raise questions that would take decades to even begin answering, to detect an unexplained hum in the plasma between the stars, an unexpected wall of heat at the edge of the solar system, or a magnetic bridge between our sun and the wider galaxy. And yet right now, a team of engineers in Pasadena is attempting the most complicated power management operation ever tried on a spacecraft this far from home, guided by a plan called the Big Bang, with a single half-watt motor left spinning quietly as a small placeholder for hope, working through a communication delay measured in days, trying to keep the only human-built instrument in interstellar space alive for as long as the laws of physics will allow. They have not given up. The signal is still coming home.